Good evening. It's been a while since I made a video on my hobby, studying physics. I want to do something on the fine structure constant. Why? Because I feel it's one of those mysteries that, popular books on physics, they still present it as some kind of a mystery that needs to be solved. And I really don't think it's the case. This video got triggered a bit by, I get sometimes questions or suggestions, and on LinkedIn actually I was contacted by someone who said, "Hey, fine structure constant. I developed this equation. Um, Here it is, and the meaning of the fine structure constant is contained in that equation." So he has a numerological formula there, and that's I'm going to come back to that. That's already where it goes wrong. I think pure numerological formulas have no meaning in physics. There's no physical dimension. But so he has this t factor t 2 times 8 times 18 times 32 times an irrational number, pi minus 1. Plus 8. So I'm immediately going like, okay, why don't you simplify by factoring out the 8? And then he writes alpha, or approximates alpha by 1 divided by 8 square, and then 2 times that factor t, again by pi minus 1, which he could have factored out, and another 8. So that doesn't make sense. And so I replied, I said, this is really mere numerology. And what I mean with that is that you have factors there which are not associated with any physical dimension. Some kind of SI units, energy, Joule, electrical charge, whatever, or some combination thereof. I refer them actually to a manuscript which you found on academia.edu before I started publishing on ResearchGate. The reference is there. The Emperor Has No Clothes was a manuscript that was submitted to a few publishers, but unfortunately they didn't follow through, despite the fact that we actually had a contract. But in chapters 10 to 12, I really build on what happened with the revision of SI units in 2019, where basically, the mystery behind the fine structure constant has been solved. In those chapters, I offer insights into, where the fine structure constant pops up and why it does so in very different contexts. So the point is, it's no mystery that needs to be solved. The fine structure constant actually has no physical dimension itself, which is actually normal. It's a ratio, a combination of nature's constants, which it is. The definition, I put it here. You have the magnetic and electric constant, which are equal to 1 divided by c squared. You can get it out of wave equations. And then the electric constant is defined as the square of the electric charge, the unit charge, divided by 2 times that fine structure constant times Planck's constant times the speed of light. And the magnetic constant, through that first formula, the product of the magnetic and electric constant is 1 divided by c squared. You get then that the magnetic constant must be equal to 2 times that fine structure constant times Planck's quantum of action, divided by the square of the unit charge times c. So the magnetic, what comes out of it is the magnetic and the electric constant and the fine structure constant are sort of, co-defined, and they reflect the same thing. So it's not that from one constant you get the other. No, it's a set of physical nature's constant, the unit charge, Planck's quantum of action, c, and from those you get, and these three equations, you get these three constants: fine structure constant, magnetic and electric constant, simultaneously. And that's why if you go to the codata, the relative uncertainty on those measurements is exactly the same, plus or minus 1.5 times 10 to the power minus 10. That's a lot of zeros behind the decimal. But those formulas do make sense, of course, and I said they do have a physical dimension, electric and magnetic constant. but it doesn't give really the physical meaning. So that's why I want to talk a little bit about that. What does it all mean? I think alpha pops up in very different contexts. The first one is really a bit as a scaling constant. As you will probably know, an electron has various radii. We have the Bohr radius, which is sort of real average distance from the hydrogen nucleus, the distance between the electron and the hydrogen nucleus. That's the Bohr radius, and that doesn't have the fine structure constant. It's just the h square divided by the mass, or the equivalent mass of the energy of the electron, times the unit charge. So the unit charge written in all units, if you translate it into the current day SI units, then E square is the unit charge measured in Coulomb squared divided by 4 times pi times the electric constant. And then we have the h bar squared and the mass of the electron again. Now, it turns out that we can write that in terms of the Compton radius of an electron. We say the Compton radius. I've heard about a Compton wavelength, but no, actually the electron does have what Professor Dr. Leclerc calls the scale above which the electron can be located in a particle-like sense. So if we sort of beam light on it, there is a scattering radius, and that's the Compton radius. I will talk about sort of a radius and a wavelength separately. It's kind of strange that people talk about a Compton wavelength instead of a Compton radius, because for an electron, a massive, not so massive, but a matter particle which has a mass and charge, it has a radius. It's not some kind of zero-dimensional thing. Things with the zero dimension whatsoever don't exist. I said that a couple of times already. But so you can write the Bohr radius as 1 over alpha, which is about 137. That's sort of God-given number, as they call it, but it's not mysterious at all. So you have that relationship between the Bohr radius and the Compton radius. And Compton radius is also h bar divided by m times c, and so times 1 over alpha gives you the Bohr radius. We also have a third radius, and that's an interesting one. The classical electron radius, as it's called, or the Thomson or Lorentz. When you when photons are beamed on an electron, usually in a crystal lattice or some material, or not in free space, but on hydrogen atoms, diatomic molecules. Then sometimes they scatter inelastically. Compton scattering, usually the photon gets absorbed, gets re-emitted, and the re-emitted photon will have a different frequency, different energy, and the difference between the frequency or energy of the emitted photon and the absorbed photon, will give the electron some kinetic energy, which may lead it to sort of leave the hydrogen orbital and become a free electron, or go in some other direction. So that's a context where alpha pops up as a scaling constant, and I will explain why in a moment when we talk about the third physical meaning of the fine structure constant. I noted here the formulae, so you can check actually. So that's the definition of the fine structure constant. You can see it is defined in terms of physical constants. The square of the unit charge, again, the electron charge, divided by 4 pi times the electric constant times h bar times c, and you can also express it through the formula. Electric magnetic constant is equal to 1 over c squared in terms of the magnetic constant. So it's clear that let me quote. I'm going to look on my screen here. There's this book I'm going to talk about it, the strange theory of light and matter, which is one of the more very popular books on quantum electrodynamics. And And there you will write at something like, where does this number come from? The fine structure constant. Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. We know what kind of dance to do experimentally to measure this number, but we don't know what kind of dance to do on the computer to make this number come out without putting it in secretly. That's so much nonsense, and it made me actually look up where Richard Feynman's book. I'm quickly going to show it before I go a bit deeper here. QAD, the strange theory of light and matter. And I was wondering, like, really, would that be something that Richard Feynman would have said? And it turns out that this book was actually written by a non-physicist, Ralph Layton, the son of a famous physicist, actually. And it's a transcription of 4 very short lectures that Feynman gave actually a few years before he died to one of his acquaintances. So I'm sure he did not have the time to probably reread what Ralph Layton made of his lectures. I'm going to talk later about it. There's a lot of stuff in that book that makes sense, but this kind of talk that the fine structure constant is something that remains to be explained and kind of magical. So the God's number, that's nonsense. The fine structure constant also pops up in the context of electron-photon coupling constant. I will show in a moment. Not exactly how, but a bit better than what I explained here. So yeah, it's sort of a probability amplitude, and if you take the absolute square of a probability amplitude, you get a probability. So once a photon is on the same spot, and we can talk what is a spot. It's not an infinitesimally small point, but sort of once a photon is in, indeed within that scale. Within that scale, under the scale above which the electron can be located in a particle-like sense, there's a high chance that there will be scattering, hard scattering or elastic scattering. And so alpha pops up as a coupling. So when does the electron and the photon, when does the electron actually, what is the chance that an electron actually absorbs a photon or emits it? So here I wrote a few things down. I think one thing, let me start by the bottom actually. You should remember a photon is a traveling field. It's not a traveling force. At the same time, a photon has an energy. In a way, it's, when you talk about a force has to act upon something. And we all know in the context of quantum electrodynamics, and we all context the thing that a force acts on. In classic Newtonian physics, it's a mass, but then in electrodynamics, it acts on a charge. So a photon carries no charge, so it cannot be a traveling force. It's a field, a traveling field, and I'll talk about how you need to think about it. However, a photon does have energy, and I'll talk about how that energy gets expended. Once it gets absorbed by an electron. And energy can always be written as some kind of force over a distance. So we might have a formula here. I'm just taking you sort of to the gymnastics of math and how we can think of that fine structure constant as a coupling constant. So we might think of the energy of a photon. So let me circle it here, red, purple. The energy of a photon, we might write it as some kind of force that we associate with that photon. Photon can have different energies, of course, different frequencies times some radius, and you'll say, oh wow, a photon has a wavelength, but why would it have a radius, and why do you write it? Why don't you write it as a wavelength? We'll talk about it in a moment. So we would have a formula which says the energy of a photon is equal to some kind of force, the wavelength, a distance which is equal to the wavelength of that photon times 2 pi. So that would be the radius that we would associate. We know photons have a linear wavelength, some kind of radius. And let me go straight away, actually, sort of to this figure here. which I borrow from Giorgio Vassallo, in which he shows this figure. It's in the context of actually, he thinks of a charge that is, oscillating around. You can see here, around and around and around at the speed of light, and that's how we actually imagine an electron. Actually, some point-like charge inside, point-like but not dimensionless, goes around and around and around. Now, if you add a lateral component to its velocity, so here we have a radial velocity equal to the speed of light. It's still, the speed of light is going to be distributed over a radial component and a lateral component, a linear aspect of it. And so the more speed of velocity, the higher this horizontal velocity, the linear velocity becomes. You can sort of see that the radius, all right, the radius has to become smaller, and that's sort of where I'll let you think about it, and I got my papers, but where you can see that clearly, any kind of wavelength, talk about the Breuil's wavelength in any case, you can sort of associate it also with what I would say a radius of motion, because this geometry is actually the geometry that we are thinking of in the context of an electron. This will be a bit Chinese, but just bear with me. For a photon, the Breuil relations apply easily. We have this here. We can associate some momentum, some pushing momentum with a photon. I will explain how that works. Once an electron absorbs a photon, as said, it will acquire maybe some kinetic energy, and it will be equal to the difference between the energy of the incoming and the outgoing photon, two different photons. And a pushing momentum, what happens will obey that this relationship. That momentum times wavelength, a wavelength, will be equal to Planck's unit of action. And in the case of a photon, we know that the momentum of a photon, I will show you how you can think about the momentum of a photon, but it will be equal to the energy of that photon divided by c, times then this wavelength, and that wavelength is equal to h times c divided by e, which e over c is h over p. That's h divided by p. There we go. Yeah. The second Breuil relationship is the energy of a photon times its cycle time will also be equal to the photon will pack 1 unit of Planck's quantum of action. So that's what it packs, one unit of h. And so you can rewrite that as the cycle time is equal to h divided by the energy, and that would be equal to 1 divided by the frequency of the photon. The frequency determines the color, just like the energy. So the point is here that R, if you wonder what it is actually sort of what we call a reduced or an angular wavelength. It's just the linear wavelength of the photon, and I'll explain what that linear wavelength actually is in a moment, divided by 2 times pi. So here we sort of mathematically, physically, intuitively, if you lost me already, it doesn't matter. But we've explained actually that that lambda as this linear wavelength, and or because it's just a division or a reduction by 2 pi in that formula here, the E times the energy is equal. Let me try to clean up a little bit my notebook. Yeah, that looks better. In that formula here. But so we're still like, well, what is this force? Again, what I said, a photon is a traveling field. It's not a traveling force, but of course they are related. A field sort of makes abstraction from the charge on which a force acts, and vice versa. You can say sort of, if there would be a charge, and that's where I'm going to come, then the force that would be associated with the photon would be equal to that, and that's actually the interpretation we want to give here. I hope it becomes clear with this picture actually. So yeah, we say like, oh, force associated with a photon. I mean, there's no charge. We must ask the same question actually for the momentum. What's the momentum of a photon? What is the p in that the Bray relationship, which says that the momentum of a photon times its wavelength should be equal to 1 to Planck's quantum of action. Well, think of it like this, actually. So we have this figure here. So we have incoming light, and we know it's a beam of photons. Let me explain what a photon is. So a photon is sort of a, a traveling electromagnetic field. We have an electric field vector, and we have a magnetic field vector. And we know that one goes up and down, this one moves in and out, as this photon moves to space. So we basically have an electric field vector at some position x, y, z in space at some point at t. And we have a magnetic field vector at some point at x, y, z, the same. We're talking about the same. At the same time. Okay, now these two fields, this is the thing why a photon, it has a linear wavelength, which I'm going to explain in a moment, but these two fields are zero everywhere, except where the photon, of course, happens to be at point t in time. So it's point-like, and what's the wavelength then? Well, that's the distance between 2 points x, y, z, and another, x1, y1, z1, and x2, y2, z2, for which the E and the B vectors have the same value. I will refer you to my manuscripts for visualizations, but that's basically it. Where we also know that the speed, the velocity of propagation of a wave and of a photon is the speed of light, and that's equal to the distance that is being traveled between 2 points where the electric and magnetic field vectors are the same, and then the time that is needed to travel, which is the cycle time. And so that's then that linear wavelength divided by t, and we have that nice formula where the velocity of a wave, propagation speed, is equal to its wavelength times its frequency, because of course the cycle time is 1 divided by the frequency, and so the frequency is 1 divided by the cycle time. I clean up again. So we can say a photon packs energy, and that energy is given by its frequency multiplied by Planck's quantum of action, or reduced h bar times the angular frequency. And from there we get that other formula, the energy times the cycle time is h, but it also packs 1 unit of physical action. Physical action is actually something that they should teach a lot better than they do. They usually don't talk about it, but it's it's a force over some distance during some time, and it's in German it's called Überreckung, and the h actually comes from a Hilfsvariable that Planck needed to develop his theory, and he saw that the Überreckung, he called it Überreckung, and Einstein also analyzed that a lot. But so what happens is this here. We have that photon that is coming in, right? Nicely equal, right? This is the wavelength. When it's here, the E and B vector will be here. When it's here, the E vector will be smaller, and maybe it will be bigger. It's smaller, so it goes in and out, and then it hits here an electron. And I'm going to talk what an electron actually is. So because at that point, when it interacts with an electron, let's suppose we have the electric field vector pointing this way, and then we have magnetic field vector nicely orthogonal to it. So the electric field vector will, just have an electrostatic force on the electron because there's a charge. So we have a force, the photon, the fields that are associated with this photon, accelerating this electron and giving it certain velocity. Force gives an acceleration. The electron has a rest mass, so it's not going to be equal to the speed of light. So then we, of course, have a magnetic force. We know as soon as a charge has some velocity, the charge is the unit charge, then there will be a magnetic force, which is equal to the vector and the cross vector of product of the magnetic field vector times the scalar product of the unit charge times the velocity. So the total force is, of course, the addition of both. So now we can write something very funny, and I also actually struggle with it a little bit. So we talked about this energy of a photon. We talked about this photon radius, so the radial equivalent of its linear wavelength. We have the same for the electron. We can have a Bohr radius, because that electron here, of course, will be part of some atom in the crystal lattice. So it will be orbiting around something else, and it's really an accident that that photon hits the electron, because it could have been there, or it could have been there, or it could have been there, and that's where we're going to talk about why that alpha pops up and Compton scattering. Is a certain probability, it just goes through the atom in that molecular or crystal lattice, and that it doesn't hit an electron. But if it does happen to hit an electron, then this is what happens. So if that's what happens, then the Bohr energy, we know the energy of an electron depends on the principal quantum number n, and read that manuscript. The Bohr energy will depend on that principal quantum number, the orbital, the first, the second, the third. And it will diminish as it goes out. Free electron has less energy. It has more energy, sorry, it will be lowering bound when it's closer to the hydrogen atom, combined for a system with less energy. But that's the formula for that Bohr energy, 1 over n square times alpha squared, it pops up there, times mc squared. And then the Bohr radius, that's also sort of formula from the Compton radius, is indeed h bar divided by nc. In the context of an electron that's orbiting a hydrogen nucleus, we have to add this factor here, n squared. So that cancels out, that cancels out. We have an alpha that leaves. And then we have this here, the energy of the photon, and then the radius, as I showed here. In this formula, we can develop a formula for the radius in terms of the energy divided by the force. Page. We will have that formula, so the energy of the photon cancels that out, and indeed you have alpha. So that's a funny formula, but it explains this sort of this coupling between as a coupling constant that it really depends on these energies of the Bohr radius and the photon radius, and then the energies and then the radius that is associated with those energies. Said more energy for a photon is shorter linear wavelength, higher frequency, and etc. Bohr radius also, if it's on the first or second or third electron shell, you have a different radius. And so what does it mean really? It's this physical dimension of an energy times radius is a weird one. Its physical dimension is Joule times meter, and Joule is Newton meter times meter is Newton meter square. So what can you say about that? Not very much, actually. It's quite abstract. It's going to become a little bit less abstract in a moment. But it's the same thing as angular momentum times velocity that also yields a Newton meter square. So we can write alpha also in terms of angular momentum that we associate with the nth orbital of an electron time classical velocity of that electron. And then, some kind of angular momentum of the photon times its velocity, but its velocity of the photon is c. And, you can write it all out. Here also, we're going to have the c that goes, the c that goes, the n that goes, the h that goes, and we have alpha. So all these formulas make sense, and it's just what I'm saying. It's not numerology. All these factors have physical dimension, but they cancel out and give us a pure number, alpha. We can also write it in terms of the physical action that we would associate with an electron in orbital times its classical velocity again. And the same here, and you also get alpha. This all sounds very mysterious, but less, much less mysterious than saying like, this formula. Where do these numbers come from, right? That doesn't make sense. Sorry to say that to the person, but I think it was friendly. What else to say? I can't clean that up. It's a pity. So let's go to that book now, actually, where, the strange theory of light and matter. I said a lot of stuff makes sense in that the little book. If you want an easy book with not too much math, it develops a very intuitive metaphor of a probability amplitude, because people struggle with that. The absolute square gives us a probability. I sort of demystified it in my works, but that's complicated to do that, and it does require math. It does require an understanding of complex numbers. And so he develops this metaphor of a stopwatch with one hand, and this hand has a certain length, a magnitude, and has a phase velocity. So he avoids what I write here. Complex number, we can write it as Euler's number to complex exponential. Here's the phase, and then this magnitude, which is the magnitude of the complex number, times the same thing. We can write it as cosine, and the sine multiplied by the imaginary unit, and so on. The thing with the imaginary unit, and that's what I if I would write a book like that, it doesn't take too much genius to explain that I, imaginary unit, amounts to a rotation. It's a rotation operator, and it rotates by, let's say, by minus 90 degrees. If you associate the minus sign with a counterclockwise rotation, so 2 times it would bring you to -1 in the previous. And that's what I always say in a lot of stuff about probability amplitudes. It matters if you go if you rotate something in this direction, you arrive at the same point. So this mathematical equation that you have, that e to the complex exponential plus I times p, is -1, and then we have e minus, and we arrive at -1. So mathematically, yeah, it's the same, but physically it's not. And that's something that I would hope that future popular textbooks point out, because it eliminates a lot, and then you can start talking about rotations and rotations. But the good thing about the book is, I think it does provide like a good analytical framework for to understand how photons behave and electrons behave, and how quantum math actually works. I call it the 3 building blocks of QIED, and these are really well explained in the book. You have a probability amplitude for a photon to travel from point A to B, and we write that like that. And we have a probability amplitude for an electron to travel from A to B. And then we have a coupling constant, or a junction number, when an electron and a photon happen to be on the same spot. What is the probability or probability amplitude to absorb or emit a photon? And there I said, the fine structure constant comes up to be precise, because we're talking amplitudes, and we get the probabilities from taking the square of their absolute value. You actually get a root factor of alpha. So that's the number. It's actually minus. You have a plus and a minus of a square root. This minus is very confusing, and I would have hoped that they would have explained that in the book as well. It really corresponds to a rotation by 180 degrees. We just move our stopwatch half a turn. And you get that with Compton scattering, elastic or inelastic scattering. That minus sign is there to illustrate that actually the photon, it sits there a little bit, and there's other stuff, and that explains the magnitude and the minus sign. But this is a complex number. Probability amplitudes are complex numbers, and they don't get added; they get multiplied with each other. Let me clean this up and go to the last. The third context, and it's a bit the same, where fine structure constant pops up. This context is indeed what I said with Compton scattering. Compton scattering is exactly the same as know what happens, what I told you, it's photon-electron interaction. And sometimes the scattering is inelastic, sometimes it's elastic. It's inelastic, it's sort of the ingoing and the outgoing photon have the same energies and the electron stays where it is. If it's elastic, then they have a different frequency, and some of the difference, the difference in the energy gets translated into kinetic energy of the electron, which makes it jump from one orbital to another, or even, cuts the electron loose from the nucleus altogether. So how does this work? That's our electron model. Maybe I'm going to pull up now some of my publications. Let's see here. Yeah, so this is the book. Sells really well, but I said don't read it. Also, don't read Feynman's lectures. I'm sorry to say, read my stuff. My lecture on physics. I have a lot of publications there, but that's sort of where we think of an electron as sort of a charge, but it's charge in motion. We think there's like a core inside that. Let me go back to my illustration here. To this one here. We think really of if this would be an electron, then the electron would be there would be some kind of core charge, much smaller than the Thomson radius, that goes round and round and round, and if the electron moves, as I said, the radius of the electron seems to become smaller, and that's really what explains the scattering. When the photon hits that hard core, then and it gets scattered. Otherwise, it messes with the electromagnetic fields that keep that oscillation going, and you have a different dynamic. So if we take the electron itself, so we have this Compton radius, and we think of really a charge going around and around and around is the electron, and so that creates it's a tiny ring current, and it will create a magnetic moment, which will be up or down depending on the direction of the core charge going around. It will go one way or another. So we would have a theoretical magnetic moment that would be equal to the current times the surface area, or the area. So the current is of course equal to the charge, the point-like charge, times the frequency that goes round and round and round. And the frequency is because we think of that point-like charge inside as going around at the speed of light, c divided by 2 pi times the radius, the Compton radius, plastic radius. So times the p square here, and that one goes away. So we're left with a, and we said that's the Compton radius. So we're left with a QE here that we have c divided by p goes this. So we have this theoretical magnetic moment that we can associate with an electron, and it's about this value, minus, because it's negative charge, minus 9.27401, and then a whole series of smaller decimals times the Euler, this physical dimension, Euler times the inverse of a Tesla minus 1. And then, when we measure actually, and it's remarkable that we can actually measure that, so the codata value is the most precise, or a combination of all measurements that have been made, and the most sensible guess to what the actual value would be in light of all these experiments that are very precise. Experiments that are more precise, of course, get more value in this weighting. There you have minus 9.284764. You see the preciseness of this thing here. But you can also see that there's a small difference, 2827. It's not the same. So this difference is the anomaly, and it's measured like this. The difference between the measured value, the theoretical value, as a percentage or a ratio against the theoretical value. And we know that that's sort of a Schwinger's factor. plus something. I think it's 0.05% or something. But yeah, again, here this alpha, this fine structure constant, and all the mysteries about wow, where does that come from, or God's number. This anomaly is not an anomaly at all. If you do think logically and say like zero-dimensional charge cannot exist. There's no such thing as a zero-dimensional charge. No such thing as a zero-dimensional charge. So we must distinguish between. Oh, I haven't got that figure here, but you have something going in a certain radius. This is the quark. This is the electron, right? The whole. You need to think of an electron not as something static, but a quark charge inside, and if you take the geometric center and then the effective center of that quark charge, you will see that there's a bit of difference. There's more charge. Let me make a nicer drawing. Different color. This is the geometric center. You see there's some space here. There's actually more charge outside than inside of the theoretical radius. So you would say like, oh, that's not possible. It needs to move inside a little bit. So, I mean, it's complicated geometric argument, which I develop in my papers. But you can see that you need to distinguish between an effective center of a charge in motion and its geometric center. And then there's an iteration process where you sort of adjust your theoretical radius, your theoretical magnetic moment, and then you do another iteration, and that sort of explains why you have a formula with various factors and various preciseness where the fine structure constant pops up. This is a bit rough and sketchy. I realize that, but that's all. That's all what there is about a fine structure constant. It's surely not a mystery, that needs to be solved. It has been solved. There's nothing left to be solved. So that's it. I will stop here, and I wish you a very nice evening. I guess this lecture was probably not as clear as the others, so I recommend maybe to listen to the others. But it fills the gap. I never talked really about this fine structure constant the way I've been talking now about it. It brings together a number of things. But so Feynman's QED. Where does this number come from? Nobody knows. It's one of the greatest damn mysteries of physics. A magic number that comes to us with no understanding by man. We understand everything. I mean, physics is basically, I said that, dead as a science. The physical principles are all well established. We can explain everything. That doesn't mean it's the end of applied science. This bioengineering, nanotechnology. There's so much stuff and so much things to be explained. Also, what goes on inside of the nucleus. Nuclear force. I also think it's electromagnetic, but so a lot of stuff has been explained there. So in my papers, maybe can do that. Quickly walk through them. That's the one on. Let me see, but yeah, number 10, structure of electron protons, the radius, the size of a proton can be explained. The Lamb shift, explaining the Lamb shift, that's also sort of some kind of mystery where Lamb himself at the end of his life wrote like, oh, I did the experimental discovery, and what the theorist made of it is kind of hellish. At the end of physics, Defoe was. But have a look at that. I think it's all interesting, but there's a lot of practical puzzles that have to be solved. But I think there's no mystery in fundamental physics anymore. And that's an opinion, and I sort of stopped doing research because I think I do have the answers in these papers. But of course, You can agree or disagree and send me feedback, but yeah, maybe to go back to the original thing. Formula like this, you know, I can't do anything with that, and I will not even examine it really, because you know the meaning of the fine structure is constant, is contained. I mean, there's no physical dimensions, there's no geometry, there's nothing there. So so that's it. I thank you very much for your attention. Let's see how long I talked. Probably too long. Get to here. 45 minutes. That's kind of fine. Have a nice evening. Have a nice weekend, and enjoy.